Yeah, my name's Ray. I'm a Pythonista. I've been writing Python for quite a long time. So what this talk is about, it's about how to solve hard problems. So, I've been speaking at various conferences for a while, and, there's a lot of library talks. There's a lot of talks about, how to use this library or, these features in Python. But there's not a lot of talks about how to approach solving something that's really hard or seems sort of overwhelming to solve. So this is a little bit of a story about me solving something that I felt was insurmountable, that in a lot of research that I did felt insurmountable. And so I'm hoping to kind of give you guys kind of an idea through my journey of solving this problem, and then maybe give you a framework so that you can also solve the problem, similar problems or also tough problems. We're going to go over a little bit how the algorithm works. I'm going to talk a little bit about some more potential uses of the algorithm. I'll show you a quick demo, both of like the pure implementation of the algorithm, and we'll kind of talk through it and what it's doing. And then I'll also show like it in a production system. What this talk is not about is Python libraries. It's not about computational complexity, even though I am kind of using those terms. It's not about P versus NP or any of that kind of stuff, not data structures, and I'm not even really going to go over other algorithms other than a very brief introduction to genetic algorithms. So that's where we're at. I'm not an expert, right? I'm not an academic. I don't have a master's degree. I don't have a PhD. I just recently learned what data science and machine learning is, like by taking Coursera course online. This does not use machine learning, right? So like I'm going to use terms. I'm probably going to be wrong sometimes, right? So please don't fault me. And this is also the first time I've also given this talk ever. So it's going to be a little rough, but hopefully we'll get through it. So this is me. This is my double life. So I'm a software developer. I work at Chase right now. Before Chase, I worked at Root. Before then, I did a bunch of startup stuff. And I'm a gamer, right? So I design board games. My first game came out in 2016 by Artana. It's called Corrupted Kingdoms. And this is important because there's someone very important in this picture, this guy up in the top right. His name is Nils Hertzman, and he is sort of a mover and shaker in the game industry. He's a reviewer, but he's one of these people that knows everybody, right? And so in 2016, I was talking to him, and he says, hey, I have these friends on the other side of the convention center, and they need help with an app that they're trying to build. They run these tournaments, and they're in Excel, and it's not great, and they just need somebody. I know you're a developer, so maybe you can help them. And I said, okay, sure, I'll go talk to them. I have no idea who these people are. And then I learned it's these guys, and if you look closely, it's CATAN, right? So now I'm sitting in front of the CATAN people, and they're telling me about all these tournaments that they run. And the guy up in the top left, not top left, but the second to that, his name's Morgan. And so I've been working with him on this application for the last 2.5 years. And they want to be able to run tournaments at convention centers without Wi-Fi. And they want, a bunch of their different stores to be able to run tournaments and then kind of sync them together. And they want, CATAN has a huge tournament sort of system, right? You go to a local qualifier, and then maybe you qualify for nationals, and then maybe they ship you to Germany, and then in Germany you have this big world championship, and it's a big deal. Like they spend a lot of money on this every year. So that's what's that. So in talking with him, he tells me about what he wants to build, and I go, yeah, I could do that for you, and I'm excited. I'm a brand new designer in the tabletop industry. I want to make an impression, right? And so yeah, okay, and get the requirements. We want to manage events. We want to register players. We want to seat players. We want to generate and organize tables. We want to move people between tables. We want to be able to print out rankings and seating assignments and all this other stuff that goes into running a tournament. And I go, yeah, that's simple. That's a CRUD app, right? That's not hard. I know how to do that. So I got hacking away, and about 6 months later, I showed up to Morgan. I handed him an app, and I said, this is everything it can do. And he goes, yeah, okay, let me play with it. He gets back to me a week later, and he says, well, we got some problems. Your algorithm doesn't really do what we need it to do. Like, the core of what we need to solve right now is we need to be able to randomly seat players at tournaments in a consistent and deterministic way, right, that follows these rules, right? Some tables are not going to be 4 players. Some tables are going to only have 3 players. Some tables are going to have 2 players. Okay, there's a bunch of edge cases in there. immediately my brain's starting to go, oh, okay, what did I get myself into? And then he says these two things. Players shouldn't be seated in seats they already sat in from round to round. So if in round 1 I'm in seat 1, the next round I need to be in seat 2, 3, or 4, but I can't be in 1 again. And players shouldn't be paired against other people they've already played against. And I immediately went, oh, okay, this is actually really hard, because now I'm trying to sort and optimize into separate groups, but how those groups are arranged, right, affects the other groups. This is really tough. And they had a weird scoring system, which I'm not going to go into. So I thought about it a little hard. And in the past, I've given a lot of talks on genetic algorithms. I know genetic algorithms inside and out. I thought genetic algorithms are probably a good way to solve this. And so I thought, genetic algorithms. This is a good thing. For those of you guys who don't know, a genetic algorithm basically has 3 components to it. You have some structured data. Sometimes it's represented as a bit stream, or it really could be any sort of object. What you do is you start with just randomly generated crap in the objects, right, in this bit streams. And then you apply fitness function to it. And you say, given this bit stream, and given the properties of this object, how fit is it to an environment that I want this object to live in, right? And after you apply that fitness function, you take maybe the best half, right, of the randomly generated stuff, and you keep them, and you kill the worst half. And the best half gets to breed, right? There's a crossover function. They kind of mix up a little bit, but they're generally just modified. You make little tweaks here and there, and you run through that. And you run through that, I don't know, 100,000 times. And then at the end of it, you get something that's pretty well fit to the environment it's supposed to be in. There's a lot of problems with genetic algorithms. Back in the late 90s, early 2000s, in AI, machine learning, evolutionary algorithms were all the rage. Nowadays, it's all statistics and something that's more hardcore. And the reason for that, or more rigorous, the reason for that is that genetic algorithms are finicky, right? It's really hard to develop a solid model using evolutionary models. But I know them really well, so I'm going to go and implement it this way. So I start hacking away, right? And I present him, Morgan, here's turning man, 0.02. What do you think? And he says, okay, everything seems to look great. Let's run it at a convention. So 1 year later, after we get started, we're at Origins Game Fair. This is the CATAN U.S. National Championships. We run it. Everything looks okay, and then it doesn't. People who should be seated in seat 1 are seated in seat 1 again when they should be seated in seat 4. People that should be not paired against each other are being paired against each other. I had so much confidence in what I built, and it completely broke down. And so now I'm trying to figure out why, right? I was overconfident in my solution. I didn't test any of it because I was burnt out, and I was putting in 20 hours a week on a side project. I didn't really understand, truly understand what the problem was. And I didn't do any sort of analysis or testing of what that algorithm was trying to do. So I got kind of sad, and then I thought about it a little bit, and I thought, we need a more rigorous process. We need to apply something a little less artsy and a little bit more scientific. And what's more scientific than the scientific method? So scientific method, you ask the right question. You try to understand what is it that you're actually trying to solve. You gather information. You read a ton of research, right? You try to, that's all about that gathering information. You're not just trying to observe results, but you're also trying to see what other people have done. Then you think really hard about the problem. Make a good educated guess. You test your guess, and then you analyze it and repeat, right? And you do that over and over again, and hopefully you get to a good result. And it tends throughout history, ever since we started scientific method, it works really well. So I try to understand what really is the problem. The problem is that I'm basically trying to organize groups when the organization of the groups themselves affect how other groups are organized. I'm trying to do an optimization problem, right? I'm doing almost a sorting problem. And I thought through all these different things. And then I also thought, why is the thing that I built not solving that problem, right? And I thought about this really hard. And I did a lot of research. I read a lot of different papers on people trying to solve grouping problems, matching problems, marriage problems, different kinds of optimization problems. I must have read 20 different research papers. And then I did what every programmer does, and I go on Stack Overflow, and I see a post. And on that post, there seems to be a very clear proof that this is an NP-complete problem. And I went, I kind of suspected that. But, this is what goes through my mind. Right? And I went to bed. I was hopeless. There's no way. I was hopeless. And I went to sleep. And I woke up the next morning. And I said, I made a commitment. And I got to do this anyways. So I thought really, really hard about the problem. Really hard about the problem. I spent at least a few weeks thinking really, really, really hard about this problem. And after thinking through it, I thought, I know how I'll solve this. Genetic algorithms. So that's where I started, because that's what I had, right? That's where my knowledge base was. And around the same time, I was taking CS 223 online, which is the Stanford machine learning course. And I was trying to understand what, that world is like, because it's the new hotness, right? And I thought, maybe if I apply some of the things I learned in that course and some of the research that I read, and I keep iterating on this, I'll get to a solution. So I hacked away, and I came up with testing strategy. I wanted to simulate lots of tournaments at once, right? I wanted to simulate the whole thing, and I wanted to have some sort of verification in place from round to round. Is there anybody, because it's very easy to check, right? Is anybody played against somebody they played against previously? Simulate all of that stuff, and then I also wanted to develop an objective measure of success. And that's really important, and also one of the reasons I started with genetic algorithms, because you have an objective measure of success. It's your fitness function, right? You score the fitness of an entity, and then that tells you how well they are to the environment. So that's an objective measure of success. If I score every entity in my system, I can tell, and I can score every single table, and then I can score the round. If it's got a really negative or really high score, in the case of this algorithm, then I know it's not doing all that well. I also decided, because originally this stuff was all written in JavaScript, it was Electron stuff, I said, well, I know Python really well. I can do quick and dirty. It's great for data manipulation, great for doing these sorts of research tasks. So I'm going to use Python. These are the things that I used. I used the statistics module so that I can understand things like deviations, variance, things like that. Matplotlib, which we'll see a little bit later. cProfile. cProfile is a lesser-known module in Python that actually is a code profiler for your code. It will tell you how long certain functions are taking. It will tell you what the CPU usage of certain functions are, what their memory usage, all that kind of information statistics can be really useful in trying to understand how performant your algorithm is that you're implementing. So that's another objective measure of success, because the hidden requirement of this is it needs to be fast, right? It needs to be almost instantaneous to the user. Obviously, it's not. And then I wrote some custom tools to gather some more stats. And then I used Matplotlib to analyze the results. So what we're seeing here is on the left, you see the fitness score, right, for one round. So we're looking at one round here, and this is the value, or from iteration to iteration, how that score decreases. And so that I try to analyze my different implementations of this algorithm to see how well this dropped. How fast did it drop? Did it get stuck in a local minimum? Right? Did it hit a global minimum? And is there a way for me to verify that? So this is just one tool that I use to try to understand that. But it was super useful. This is a common sort of graph that you'll see in doing linear regression, trying to do any sort of gradient descent, right? Where you're trying to understand from point to point how do you descend. So this is kind of doing something similar. And then I would look at that, look at the results of those statistics, make changes to my algorithm, think really hard about it. Why is the algorithm behaving this way, given what I just did, and what can I do to make it a little bit faster? What can I do to improve it? What can I do to keep it from getting stuck, right? Analyze the results. And I did that. I spent 2.5 months unemployed working on nothing but this. I incorporated new knowledge. I keep going out reading more research papers. A few of the things that I considered was actually taking some of the machine learning stuff. Maybe neural networks is a good use for this. I looked at other evolutionary algorithms, things like simulated annealing and colony optimization, swarm intelligence, other kinds of reinforcement learning, different kinds of math tricks that I could do. Things that I found that worked were the use of higher order polynomials for calculating the scores, the fitness scores. This is a trick from multiple linear regression that allows you to kind of get a better idea or better score. I actually don't have any idea how it works. It's just something I learned from CS 223. Thank you, Andrew Ng. Simplifying the algorithm. I got that from some ideas from simulated annealing. And then, thinking about the problem before I go to sleep. And that's kind of when a breakthrough occurred for me, which I'll talk about later. And then perseverance. So I kept hacking. And then I had Turning Man, version 0.03. And I go hand it to Morgan. He looks at it. There are a few other bugs, but overall, it seems to be working okay. And we go to Origins this year, just a couple months ago. And it was really bad the first day, because even though I put so much effort and focus on this algorithm, the rest of the app kind of had other bugs. And so I spent all of Friday while a tournament's going on right next to me, sitting on my computer in the CATAN room, hacking away, trying to fix these bugs. But we did actually have a success. Every single one of their tournaments did seeding correctly, had everything working correctly. People were being shuffled around the way that we expect them to. So let's talk a little bit about the algorithm. It works like this. The first thing you do is you seed everyone randomly. So you generate tables. I should probably put that in there. You generate a bunch of tables. So I have a table of 4 players, then 4 players, and 4 players, and then maybe over here there are 3 players. And then I just say, hey, everybody go take a seat. And then I'm going to score each seat, each individual person in the seat for its fitness. And I'm going to walk up to each player with a clipboard, and I'm going to say, okay, have you been in this seat in the last 3 rounds? Yes, you get a point. I don't know what happened there. Yes, you get a point. Okay, that point's bad, right? Are any of your competitors right now people you previously played against? Yes. Okay, that's bad. That's a negative mark. And I do that for every single person at every single table. And then what I do is I take everyone that has scored higher than the lowest score. So if Jimmy over here scores a 4 and everybody else scores higher than a 4, Jimmy stays put. Everybody else gets up out of their chair. They go stand in a line. And then I have the first person in each line. It's basically a queue. And I have that person go sit in every seat. And I test them again all the way through. Right? Which so far doesn't sound like I'm really improving it. This is kind of n squared, right? Like I'm going through this, in not a great performant way. But if they sit down and they find a really good seat, or they have 5 seats and they're like, hey, all of these 5 seats are pretty good, you say, okay, take one of them randomly. I don't really care. They're all good. It's all an improvement for you because your score is now lower than what it used to be. And then if somebody's already sitting in that seat, they get dethroned, and I put them in a separate list. And then we iterate through all the people that were in this line, and then I tell these people to go sit down randomly. And then we iterate. Now, there's 2 very important things about this algorithm. In each iteration, the people with higher seeding scores are guaranteed to improve towards the global minimum. Those people that get up in that line, this was this late night kind of realization. Those people that get up in that line, they're in that line because they had the worst scores. And so if each single person goes and sits down and they're picking their best scored seat, they are improving. Similarly, because of the nature of this line growing bigger, this line grows smaller, right, that gets dethroned. In each iteration, the people that are dethroned, they're guaranteed to decrease. Those 2 things leads to order n log n. So the worst case scenario for this algorithm is it's order n log n times order n plus order n squared, right? The best case is the one on the bottom. Again, I suck at math. This is what I remember from college. If you know better, come tell me, because I want to know what it actually is. Other uses for this work. So a table is a group, right? It's a group of 4 people. A seat is a membership. It's just a node within the group, and a player can be any object. This is basically a constraint-based grouping problem, where the structure of one group affects all the other groups, and where the constraints are based on the group structure itself. So any time of problem that we have where we need to sort things into groups, but those groups are interdependent based on structure, this algorithm will solve for you. So let's go through a demo. It's going to be a pretty quick demo. What we're going to do here is we're just going to run my test. This is more of the raw version of this. So this is round one. Round one, there's no history, right? Players just get seated randomly. Obviously, they're in the best seats because they haven't been in a seat before, right? So we just see it automatically goes to 0. The next time starts with 274 people, and then you see it decreases pretty rapidly, right? And if we go and we look at this real quick, the score for for a higher iteration, let me see if I can remember TMUX. No, the scores are deterministic. So each when I go and I score a seat, I can show you, if we have time, I can show you the scoring code. But I actually look at that person and I say, the other 3 players here, have you played against them previously? For each person you played against previously, that's a point, right? And the points are bad. I want to go to 0. So higher is worse. And then you're in seat 1. In the last 3 rounds, have you also been in seat 1? Yes. Okay, that's a point. How many times have you been in seat 1? That's a point, right? So that's how I'm determining the scores. And you can see in this first iteration here, the number of seats that are correct. And by the way, in this, it's kind of misleading. But correct is you have the lowest score. Not necessarily it's the perfect, right? So correct would be there are 726 people that have 4s. They're not 0s, but they're 4s. But the other people that haven't been seated are not in the best seating for this particular iteration. So the score is really high, 1210. And then we see in the next one it drops exponentially. So of 274 people I had to reseat, in the second iteration I only have to reseat 72. Third iteration, I reseat 15, right? And the score for the aggregate score for each of the seats goes down every time until we get to the very last one. We don't see 0, but that's a problem with printing. So the score is 4.59, and then it hits 0, the global minimum. So we can do this again. Let's go back over. So this was round 2. So round 3 gets a little bit more complex because we have more history. We're seating, there's more people that are not in great seats. Right? The top line, the orange line, is the number of people that are seated correctly. The blue line is the fitness, so the overall fitness score, and then the green line overlapping is the time it takes to actually process that in seconds times 100. Do it one more time. There's even more history now, even more constraints.
Are you running this in pure Python, or are you doing external libraries for Python?
This is pure Python. And it's just because I needed something quick and dirty. But if you did this in something like NumPy or found a way to vectorize your calculations, you could speed this up even more, definitely. So here's another one. We have a lot more iterations we have to get through. It maxes out as 1,000. That's just what I have, but you can have it. I've never seen it get there in this particular version of the algorithm. It usually stops consistently around 20 to 40. And so you can see it descending. All right, so I'm going to close this, and then I'm going to show you guys Turning Man of it actually in progress. Thank you. I want to close. We'll close this real quick here. No, go back. There we go. So this is Turning Man. So let's look at an actual event. So here's an event. It's fake. It's not a real event. But we got a bunch of players registered for it. We'll add some rounds. And then I have some testing help stuff in here. So, all right. So we need to start this event. We'll go here. We'll seat these players. happens immediately. Start the round. All these players. So I told you round one's a free one, right? So this one isn't really great. Go back. Go to our next round. See the players. Start the round. Right. I do round 3 too, but I'm running out of time. I want to leave at least room for a couple questions. So future work is I want some help. Well, first off, this code is part of Tourneyman's code base. It's on GitHub. You can look at it. It's within my code repository. Let me see, slideshow. Start from current slide. It's in my code repository. You can check it out. It's GPL'd, so you're welcome to take that code and use it however you'd like, but make sure you contribute back to the community. Future work. I need help publishing a research paper. I've never written a research paper in my life. I have no idea how to do that. I would love for the community, if there's interest in this, or if you see a use case for this algorithm for some of the things that you're doing, I want to know about it. I want to publish a library that's a little bit more generic than just Tourneyman. So that's something I'm going to do in the future. That's like any particular constraint-based grouping problem that you have, this library would solve. Questions? Yeah. So in the algorithm will work with any seating arrangement that you come up with, any number of groupings. But for CATAN's purposes, they try to group in 4-player games as much as possible, and then it's just modulo math. So I go, if there's 6 players, that's 2 3-player games. If there's 7, it's a 4 and a 3. If there's 8, that's two 4-player. If it's 9, it's 3 tables, right? And so there's some very basic modulo math in there that lets me figure out. Correct. Yep.
That's what I was wondering. I was trying to decide if people were selecting if they wanted it somehow, but the only thing you care about is a list of tables.
Yeah, basically, yeah. And the constraints, right? Like in this algorithm, my constraints are: have you seeded against somebody you played against previously, and are you in a right? Right. Right. Yes. Yep. Next question. Yes.
So you did this all like just to help out, or
No, I did it just to help out. Oh, sorry. Did I do this just to help out, or am I getting any kind of fees for Turning Man? And my answer is I did it just to help out. My goal is to turn Turning Man into a project that is a platform, almost like a. Is anyone familiar with Board Game Geek? So it's a lot of Board Game Geeks in here. I like it. So Board Game is a platform that's kind of, it's IMDb for board games, right? I want to create a platform where you can go and play in any kind of number of tournaments, whether that's Magic the Gathering, or that's Catan, or that's something else, and you can go online and you can look at your rankings. I want to build a community around board game organized play. And so this was a way for me to think about how to build that, and the opportunity presented itself, and I have a lot of respect for the Catan people, and I have a lot of respect for the people in the tabletop gaming industry. So, that's it. I'm afraid we're out of time.